Hi everyone, so this is a shorter unit. This is our last lesson for Unit 3. So this lesson is on natural logarithms. Okay, we're going to talk about some properties of natural logarithms versus the logarithms from the last lesson. And then we're going to take everything we've learned concerning exponential and logarithmic functions, whether it's log or natural logarithm, and look at equations and using these relationships to solve for an unknown variable. Before we do that, the first half of this lesson is going to be focused on the natural logarithm. So this one is one of my favorite functions, I'd say. I guess if you could have a favorite function. And I find the natural logarithm much simpler to use when you're solving equations. And the reason for that is this relies on an irrational number known as E. Okay, so E is called Euler's number, and what it is it's actually the limit as n approaches infinity of this function here. Okay, so 1 plus 1 divided by the next number. Okay, so and then that's all raised to that same exponent. It's called Euler's number. What it comes out to is actually 2.718281828, and it keeps going. Okay, so it's just like pi, in that it's an irrational number with an unlimited number of decimal places. And you'll often see it on your calculator. You might just not know what it is. So there's a log button on your calculator, and beside it, there's a button that says ln or ln. You might have read it initially as in, or the in button, and I see people call it that a lot. But it's actually the ln button. And what it is if we take the log function and the base, we set it to e. Okay, so e is a number that's available on your calculator, just like pi is. All right, so this is basically a special form of a logarithm. How we abbreviate it is if y is equal to e to the exponent x. Remember, e is the base, x is the exponent, y is what's known as the power. Okay, so that's the power, e is the base, and x is the exponent. Then if we were to write it, you could write it as log to the base of e of the power, which in this case is y, or what we show it as is ln of y, so ln of y. And you'll see here there's no base, and the reason there's no base is when you stay at the ln of a function, it's understood that the base of this is e. Okay, so the big advantage to it is that you don't have to worry about whether or not you have the right base, right? Remember in the last lesson I said log on your calculator is only base 10, but our examples covered every base you could have, 2, 4, 8, any of those bases all work for the log function. For ln, there's only one base, and it's e, and you never have to worry about it being a different base when you're solving a question. That's the biggest reason that I like it. Okay, so let's look at a few examples. This is all going to be with your calculator. None of these are ones, I guess with the exception of E and H that we'll talk about here. The remaining ones are not things that you can solve without using your calculator. So if you don't have one, pause this right now, grab your calculator, and go through these with me. So what this is simply using the ln button to solve for each of these variables. So for some of you on your calculator, my calculator is like this. Mine's a Casio. I can press the ln button and then press the number 10. Okay, so for example, B here, the ln of 10 comes out as 2.30 and then 3. There's more exponent or more decimal places. Some of you instead might have to push 10 and then press the ln button. You'll have to experiment with that as we go through these to see which one your calculator, the method it actually uses. Okay, so depending on which one you purchase in our bookstore, I know that they do it either way. Next is the ln of 3000. Okay, so in this case we get I'm going to round to 8. It's actually 8.006 with decimal places, but you can round it to 8. D, the ln of 0.5, okay? That is a negative number, so negative 0.693. Remember, the reason for that, okay, is that when it's a decimal place like that, remember, it's usually 1 over a function, okay? So next is ln of 1. So that one we should know. So remember with the log, if we had the log of any base, let's call it 2 to the exponent 1, it was 0. And that was because 2 to some exponent x had to equal 1. The only exponent that can do that is when x is 0. The same properties apply for natural logarithms. So this function, the ln function, the natural logarithm, all the same properties you're going to see that we did in logarithms, whether it's adding or subtracting them together, etc., apply. So ln of 1, just like before, is 0. Next is the ln of 0.0125. And again, a negative number, negative 4.38. Now, the ln of what this is, 2.71828, you'll notice that is actually e. Okay, so you should get very close to 1. Okay, rounding it off, you'll get 1. For h, the ln of e. Okay, so the ln of the function e, that's the same as writing the log base e of the number e. So you want to arrive at e as your final number. So e to some exponent x has to equal e. So that means x would be equal to 1. So the ln of e is simply 1. Remember, the same thing happened when you had the log of any number, let's say 10, and it was 10, that would be equal to 1. The same thing applies. Okay, so these same rules apply. When we talk about equations and solving, those are two rules that will come in very handy. So next I want to talk about natural logarithm relationships. They're the exact same as the logarithm relationships, okay? So we have when two functions are multiplied together, ln of x times ln of y. Again, I use the example 3x. So let's say ln of 3x. What that's equal to is the ln of 3 plus the ln of x. Okay, so they're multiplied together. So it's the same as adding together the ln of each function individually. If you have ln of x over y, again, using 3 divided by x, so the ln of 3 divided by x instead of 3x, it'd be equal to ln of 3 minus ln of x. Okay, so it's always the function in a denominator, I almost said denumerator, in a denominator subtracted from the ln of the function in the numerator. Okay? And again, just like we had in the past, the ln of some function x raised to an exponent, in this case k, the exponent can move behind the ln function and be multiplied by it. So k times ln of x. If we use our same example here, ln of, in this case, let's do 3 to the exponent x. That's equal to x times ln 3. So you can see that by using the ln function, you then now have x in a position where you can solve for it if you had it in an equation. It's a very important relationship to understand. So looking at a few examples, okay? So our first example is if we have the ln of 15 times 36. Now you can simply multiply those two numbers together. Okay, so 15 times 36 is 540. So you could take the ln of the number 540. Or you could keep those numbers separate and use the relationships of logarithms, which in this case would be the ln of 15, the first number, plus the ln of 36. If you place both those in your calculator, you will see that you will get the exact same answer. It might be off in the 7th, 8th, or 9th decimal place by a little bit. The reason for that would be rounding in your calculator. All right, there's no other reason. They will come out to the same solution. All right? So let's look at another example. So I want you again to use your calculator for this. Use your calculator to evaluate the ln of 5,000 divided by 1.045. And we're going to do it both ways, using the laws of algorithms and without using it. Starting with A, we have the ln of 5,000 divided by 1.045. These are subtracted from one another because they're divided. So it becomes the ln of the function in the numerator, 5,000, minus the ln of the denominator, 1.045. And if you do this, the ln of 5,000 is 8.5172. And the ln of 1.045 is 0.044, and then it goes 0.017. Okay, so I rounded. So if you subtract these from each other, you get 8.5172 minus 0.044017. Again, this is rounding. And I get 8.473183. Okay, so you'll see a little bit different when we get into the later portion of the decimal, and that's okay. That's because of rounding, right? Function in B, if we don't use the laws of logarithms, we have the ln of 5,000 divided by 1.045. So we could simply simplify the number in the ln function. Okay, so if we do that, we can do the 5,000 divided by 1.045 first. So we get the ln of 4,784.688, I guess 689 if you want to round. Okay. And if you do that, you take the ln of that number, you get the same thing, 8.473. And in this, we got 176. So you can see that it starts to get a little bit different near the end. Again, because of rounding. Both those solutions I would count as correct. Okay. Now, our next example, using our calculator, we'll evaluate the ln of 5 to the exponent 7. So we'll use two methods. The first, again, using the laws of logarithms, and B, not using the laws. Starting with A, we get the ln of 5 to the exponent 7. Okay, so remember, we can take an exponent and move it in behind. So that becomes 7 times the ln of 5. Okay, so if we do that, the ln of 5 times 7, we get 11.266. In part B, we could just evaluate the exponent inside, okay, and take the ln of that whole number. So we get the ln of 5 to the exponent 7, okay, and if we do that, it's the ln of 78,125. So that's taking 5 to the exponent 7. If we do that, we get 11.266. Okay, the same number. Doesn't matter which one you do, but these rules are important because they allow you to solve for, let's say, just this exponent, right? Because otherwise that exponent, if you have a number 5 to the 7, is stuck there, right? These laws allow you to then remove that. Okay, so if you had, 5 to the exponent 7 equals x plus 2. Okay, or let's do a better example. 5 to the exponent x equals 7 plus 2. So we got to figure out what this exponent is. How do you do it? Trial and error? No, you can do it by using the rules of logarithms. Okay, remember, you can do anything to one side of the equation provided you do it to the other. So in that same token, you could take the ln of both functions, which means you'd have the ln of 5 to the exponent x is equal to, as long as you do the ln to the other side, you can do it. The ln of, in this case, 7 plus 2, which is 9. Okay? And what that does, the reason this is important is now we can solve for this x. So using the laws of logarithms, we can have x times the ln of 5 is equal to the ln of 9. And now simply to solve, we divide both sides by ln of 5. Okay, so they cancel on the one side, and we get that x is equal to the ln of 9 divided by the ln of 5. In this case, 1.365. Okay, so this was kind of an off-the-cuff piece after this, because all of our examples showed you it with numbers in there. And you're probably thinking, well, why would I use the law of logarithms when I just have numbers in there? But it's really important when you have something stuck in an exponent that you're trying to solve. Okay, so keep that in mind when we get later on in this lesson. So my off-the-cuff solving of a function for x leads perfectly into the second half of this lesson. We're going to now talk about exponential and logarithmic functions and solving for an unknown variable. So using everything that we've learned about exponents, logarithms, natural logarithms, and their associated relationships, and solving for an unknown variables. So I've written the major pieces you need to know here, okay? We've also talked about other functions like the ln of e is 1, okay, or the ln of 1 is 0, okay, items like that. I will introduce them after we do a few examples. But each of these relationships here become very important. And you'll see that they're exactly the same. They're just written in different terminology. So on the left here, each of these relationships is a log function. So starting with the very first relationship. If y is equal to a to the exponent x, then we can write the logarithm as, remember, the logarithm is solving for the exponent. So it's trying to find the exponent here, which is x. And what that's equal to is the log with the base of a, okay, whatever the base is in the exponent. And the number you're taking the logarithm of is y, okay, so the final answer that comes out of here, or the power. For natural logarithms, it's the exact same thing, except it's the number e. This isn't just a algebraic value e that I've picked out of thin air. It is e. Remember, e is that irrational number 2.78182818, blah, 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 okay, all the way through. That is the number e. So if y is e to the exponent x, then solving for the exponent x, it's equal to the log to the base of e of y, or remember that ln button on your calculator, okay? The remaining items I have shown in here are the same relationships. If you have the log of two functions multiplied together, it's the same as the log of the one function plus the log of the second function. If they're divided by one another, so the log of x divided by y, is the log of the function x minus the log of the function y. Lastly, if you have log of some function x to the exponent k, remember you can move the k down and behind, and it becomes k times the log of that function x. The same rules apply for the natural logarithm, or ln. Ln of functions x times y is equal to ln of x plus ln of y. Ln of x divided by y is equal to the ln of x minus the ln of y, again, taking these individually using your calculator. And the ln of x to the exponent k, remember that k can move in behind the ln function, and it becomes k times ln of x. Okay? Again, something that's important when we look at solving equations. So let's look at our first example. I'm going to solve this two different ways. Right? The first method being using what we know to convert this to a logarithm. The second example I'm going to show is similar to what we did in the previous example when I did the off-the-cuff example by taking the ln of both sides. So first of all, let's look at doing it using what we know of logarithms. Remember, we know that the base, in this case, is 4. We know that the exponent is x. It's what we're trying to solve for. And we know that the power is 64. So we can rewrite this as a logarithm. So we can have the logarithm, the base of 4, and the number of 64 is equal to x. Okay? If you have a calculator that could do that, you could solve it this way, and you'd come out with x is equal to 3. I mean, looking at it by inspection, I mean, for me, just thinking about my times tables, I know 4 times 4 is 16 times 4 is 64, but it's not always going to be the case. Okay? So you could convert it to a log. The foolproof way that you can always do it with your calculator is using the natural logarithm, and that is why I like it so much. So if I had, I'll move this to here, 4 to the exponent x equals 64. Remember, whatever you do to one side, add, subtract, multiply, divide, take the ln, take the log, as long as you do it to both sides of the equation the exact same way, it's valid. Okay, that is just, it's a fundamental item in mathematics, but it's very important. So I'm going to use the natural logarithm. I'm going to take the natural logarithm of both sides. So this becomes the ln of 4 to the exponent x equals the ln of 64. Okay, remember I did it to both sides. Now I can use the rules of logarithms. This x exponent can now come in behind. So this becomes x times ln of 4 is equal to ln of 64. To solve this, I need to have just x by itself. So I do that by dividing both sides by ln 4. Okay? Again, as long as you're doing the same thing to both sides. Okay? Now in the numerator and the denominator, I have ln 4, so they will cancel. And we're left with just x is equal to the ln of 64 divided by the ln of 4. Now, all your calculators, if you have a scientific one, will have the ln button. So you can simply put this in your calculator and you would arrive at x equals 3. Okay? So again, one of the reasons it's my favorite, there's less confusion as well in terms of what you're doing with your base of your logarithm. There's no base in this, it's ln. The base is always e, okay? I cannot stress that enough. Next, 5 to the exponent x minus 2 is equal to 25, okay? So I'm going to do this using the ln method, okay? So multiplying both sides by ln. I find it to be the simpler solution. So if I do that, if I take the ln of both sides, I get the ln of 5 to the exponent x minus 2 is equal to the ln of 25. Now, just because there's addition or subtraction in the exponent, that doesn't matter. This is all one exponent. So that entire piece can now be moved down. So this can all be moved to here. So we get x minus 2, okay, times the ln of 5 is equal to the ln of 25. Okay, so we're almost there. We have a few more steps. First is the same step. We want to remove that ln 5 that's multiplied by the x minus 2. So we'll divide both sides by ln of 5. Okay, so these will cancel. And we're left with x minus 2 is equal to the ln of 25 divided by the ln of 5. Okay, so now to solve, we need to remove the negative 2 from the left-hand side. So we're going to add 2 to both sides. Okay, again, what you do to one side, you have to do to the other. So these 2's cancel, and we're left with x is equal to the ln of 25 divided by the ln of 5 plus 2. In this case, that would actually give you an answer of 4. Okay, and you can always take your answer and substitute it in to see if you did the calculations right. And if you did, you get 5 to the exponent 4 minus 2 is equal to 25. 4 minus 2 is 2, so 5 squared is equal to 25. And you know that is because 5 times 5 is 25. Okay, so you can check whether your answer is correct by substituting it back into the original equation. Right? So after we looked at those two examples, there's some additional not relationships, but just factors to consider that make it easier to simplify these equations. And they work for both the log functions and the ln. Again, I like to focus on ln because it's much simpler in my opinion to use. But we'll start it with the log functions. If you have the log of base b of the number 1, that's always equal to 0. And that's because b, remember, is the base. The exponent is 0, so it's equal to 1. Okay? Remember, if you were trying to solve and you didn't know what these were, okay, then b to some exponent x had to be equal to 1. So it has to be 0. The only exponent that for all of these cases always gives you 1, okay, is 0. So x would have to be 0. Similarly, for log of b, and b is equal to 1. So that means b to some exponent has to equal just b, the number that's in there. Okay. Well, in order for those to be equal, then x has to be 1, right? Because b has to equal b. b can't equal 2b or b squared or something like that. All right. The last one, I won't show you the proof for this one. All right. The reason I won't show you it is because it's log. b to the exponent of the log of x to the same base. Keep in mind the base here needs to be the same. So the base here is b, and the base of the log function is b. In that case, it's just equal to x. In other words, it's equal to the value within this logarithm. Okay, that's useful, and we'll show you why when I'm going to solve questions where I have x within a log function. Okay, very, very, very useful to know this one, and when I talk about the e version. Next we have the ln of e. Okay, ln of e is 1. The reason for that is, remember, ln is log base e, in this case, of e. So what that means is e to some function x has to equal e. Okay, so because your answer there is an exponent, so x has to be equal to 1. So that's why the ln of e is 1. The ln of e to the x is equal to x. The reason for that is because if you had the ln of e to the x can simply be moved in behind. So that becomes x times ln of e. And what we just learned is ln of e is 1. So that means it's just x. Okay. The last one, again, very important to know, is e to the exponent ln of some function x. It doesn't have to be x. It could be x or x minus 2 or x squared. It's equal to just whatever is inside the ln. Okay. Again, I won't show you that proof. It's a longer one. I just need you to understand these two. So number 3 and number 6 are very important ones when it comes to solving equations. Okay. So now we're going to use all of these rules. Okay, and we're going to look at a few examples. So solve the following equation for x. Ln of e to the exponent 4 plus 3 times ln of x plus 2 is equal to 12. Right? My first step here is I see that I can eliminate one piece here. So I have an exponent. I can move it down. So this becomes 4 times ln of e plus 3 ln of x plus 2. Okay? And that is equal to 12. So we know that ln of e is 1. So this just becomes 4 plus 3 times ln of x plus 2 is equal to 12. Okay? So we're trying to solve for x. So what I want is I want just the ln function to be on one side. Because remember those two important rules from the last example. E to the ln of some function, in this case it could be x plus 2, is just equal to x plus 2. Okay? So I want to be able to take the e of both sides to be able to solve for it. So I'm going to first move the 4 to the other side. So we get 3 ln of x plus 2 is equal to 12 minus 4, which is 8. Now, I want to solve for x plus 2. So I'm going to do that by removing this 3. So I'm going to divide both sides by 3. And the 3's will cancel. And we're left with the ln of x plus 2 is equal to 8 over 3. Now remember, this rule is very useful because now we have this x that's stuck here inside the ln function. In order to remove that from there, we have to take the e of both sides. So we go e to the exponent ln of x plus 2 is equal to e to the exponent 8 over 3. Okay? Remember, whatever you do to one side, as long as you do to the other, it's fine. So remember, using this rule here, okay, move it over here, we get just x plus 2 on the left-hand side is equal to e to the 8 over 3. So solving for x, we need to move the 2 to the other side. So we get x is equal to e to the 8 over 3 minus 2. If you did put that number in your calculator, all right, you would get 12.392 approximately. Okay, or the way I prefer it to be left is to leave it in this form, but you can leave it in either and I won't take marks off. Okay. Our second example, solve the following equation for x. Log of 2 to the exponent 3 plus the log of 4x is equal to the log of 4 divided by x. Okay, so we've got two functions in here with x. Okay, so it takes a few additional steps. First, I'm going to simplify it by expanding all these out. Okay, so if we do that, I'm going to start by moving, okay, the exponent outside. So 3 times the log of 2. And then I'm going to separate the 4 and the x. and I'm going to separate the 4 divided by x. So first, they're multiplied out, so they multiply together, so they get added. So we get plus the log of 4 plus the log of x, okay? And that's equal to the log of 4 minus the log of x, okay? So I'm going to now start rearranging. I'm going to first take all of the numbers and move them to the right-hand side, okay? If I do that, I get the log of x, that's all that's left on the left-hand side, is equal to the log of 4 minus the log of x, and then minus these two terms by moving it to the other side, minus the log of 4 minus 3 times the log of 2. So we see here, okay, these log 4s will cancel. Now we just need x to move to the other side. So we're going to move this x term to the other side. And if we do that, we get log of x plus the log of x, which simply means 2 times the log of x. And that is equal to our remaining term on the right-hand side, negative 3 log of 2. Okay? Remember, I have just log here. I didn't mention at the start. That means it could technically be calculated in your calculator. All right? But assume that that means base 10. Okay? So now, to solve for just log x, we're going to do the same thing we did in the previous example. We're going to divide both sides by 2. And we're left with log of x is equal to negative 3 log 2 divided by 2. Now, instead of e, remember this rule was b to the exponent log of the same base, b of x, is just equal to x. So if it's not provided, you know it's base 10. So we know that our value for b is 10. So that means that 10 to the exponent log of x, okay, because you have to assume that this is base 10, okay, must be equal to 10 to the exponent negative 3 log 2 divided by 2, okay? So that means that following this relationship, this side just becomes x, what's remaining in the log. So what we're left with is that x is equal to just 10 to the negative 3 log 2 divided by 2. And again, because this log is base 10, you could put it in your calculator. If you did, you would get that x is equal to 0.354 approximately. Okay? So remember, the same rule I used both in the natural logarithm and in the log function. Okay? So that was all I had for this lesson. All right? Again, I gave you specific exercises here. I do recommend you practice logarithmic functions and solving. Okay, that will be an important item. The more you practice you do with that, the faster you're going to get, and that's very important for your tests. If you do have any questions, feel free to send me an email. Thanks, everybody.